Hello guys, this is Mr. Udeometer and we're going to be doing the ideal. Alright, so I'm frozen. Okay, there it is. In this lab we are going to be determining how much H2 gas is produced when we react magnesium with hydrochloric acid. And in doing so, we can then use the ideal gas law to calculate the ideal gas constant, essentially. And then we can compare it with the accepted value. If we're in millimeters of mercury, the accepted value should be about 62.3 millimeters of mercury times liter divided by moles times Kelvin. So we're going to be using some devices. The device kind of has a goofy name. It's called a Udeometer. It's basically like a giant long test tube that has graduation marks, measurement marks that you can measure. And it's for collecting and recording measurement of gases. Okay, let's look at this lab setup we got. We're not going to use the hot plate. We got this ring stand with a utility clamp to hold this in place once we're actually reacting, just like so. Alright, but we'll get to that later. So, we got a beaker down here and it's filled about 3/4 full of water would be a good amount. And we have a graduated cylinder for our hydrochloric acid measurement. And then we also have this giant 1,000 milliliter graduated cylinder for when we're measuring the actual volume of the H2 gas that's produced. Alright. So first things first. One, we need to know what the temperature of the water is. Not the water, but the air temperature. And it is about 18 degrees Celsius if you just look at any thermometer. And then we got to look at the pressure right there. And it's about 768 on our barometer. Alright, so those are the two values we're going to write down, and I'll get back to you at the end writing all those numbers down. We'll walk through it together. So first off, we're going to mass the magnesium. And then we'll also get 10 mils of hydrochloric acid, 2 molar. Alright, so we go to the fume hood, get these. Alright. I don't want to put my laptop in the fume hood, so I'll put it right here. There's a decent view. Alright. So, notice how I got my goggles on. And measuring out 10 mils. Alright. I'd say it's okay. I'm like at 10.8 probably. How can you see it? Here we go. Yeah, but it's as long as I got more than 10, I just want enough to fully react this. I want to have hydrochloric acid be my excess reactant anyways, so that's not as important. And then I'm going to take a piece of pre-cut magnesium. The directions say 2 to 3 centimeters long. Although if you go on the side of 3 centimeters long, you might accidentally produce too much H2 gas that it becomes not measurable because you have more than what the tube can hold. So I'm erring on the side of about 2 centimeters. Better to have it smaller than too big. But the trouble with having it too small is it's hard to wrap around the copper wire in the Udeometer. Alright, so we're going to get the mass of this real quick, this magnesium. And we're going to be using an analytical balance because it goes to 4 decimal places instead of 2. And the amount of change we're doing, because hydrogen doesn't weigh that much, it's going to be a small change. So we need to have something that's very precise. And these analytical balances have this box around it so that air currents, it's so sensitive, will change the mass going up and down. Alright, so it looks like we've got 0.0282. 0.0282. So why don't you take a moment and write that down. Alright, so I brought my hydrochloric acid 10 milliliters with me. Got my Udeometer. Take the cap off. Okay, so it looks like there's a little bit of magnesium in here from someone else. Okay, I think I got it out. So I'm going to take my magnesium that I had masked, and I'm going to put it around my copper wire. It's my magnesium. Okay, so that can be the tricky part. So, but it's on there, kind of like hooking a worm. Okay, I'm going to put the hydrochloric acid in. And then what I'm going to do is I'm going to put distilled water, or deionized water. So I'm going to put this in this loop here to set it down safely while I get some water. There it is. Just getting some water. Okay. So now I'm going to put this in here. Alright, I'm going to make it overflow, and I'm then going to take this and I'm going to put it on top. Take it out, and I want to make sure that I don't have any bubbles come in when I flip it. Every bubble of air is a bubble of error. So I'm then going to flip it right here. Looks like I did pretty good. Secure it. And what's happening is the hydrochloric acid, got a bad view of here, was at the bottom, but it's now sinking all the way to where the top was, where my magnesium is. And once it gets down, it's going to start reacting. And we know from term 1, magnesium plus hydrochloric acid, it's going to be a single replacement reaction where magnesium chloride and H2 gas are formed. So the bubbles that will be popping up is going to be the H2 gas that we are going to measure. Alright, so this is the part that takes a little bit of time. It's going to take about 15 to 20 minutes. But doing this virtually on video, it'd be really cool if I could time-lapse it. I don't have that technology or time to figure that out, so I'm just going to pause it and fast forward life for 20 minutes, and I will come back on. I got an idea. Why don't we do the math behind this? Yeah, so I'm going to pause this video, get it hooked up for the document camera, and we'll go over all of the work behind this. Okay. Oops. Okay, here we go. What we have is 0.0282 grams of magnesium, so we recorded that when we masked magnesium. The room temperature of water, we looked at a thermometer, and it was 18 degrees Celsius. And atmospheric pressure. Oh, we said that was 768 according to our barometer. Volume of H2 of gas. We're going to wait for the reaction to kind of complete. Speaking of reaction kind of completing, why don't we take a look at it real quick. And you can't really see it on video as well, but it looks all cloudy. That cloudiness is just a ton of H2 bubbles that are all rising up to the top. And you can see at the top how there's some air, and that is actually H2 gas. So, moving right along, let's get back to the really fun part, the math. Okay. So partial pressure of water vapor. Okay. So we said it was 18 degrees Fahrenheit. (18°F), according to this water vapor pressure chart, it's going to be 15.5 millimeters of mercury. 15.5 millimeters of mercury is our partial pressure of a water vapor. Right. So now we're going to go to the back page, and we're going to start answering these questions. So the first one is write a balanced chemical equation for the reaction including states. So we know that we're taking magnesium and reacting it with hydrochloric acid. It's going to be a single replacement reaction. The two positive entities, magnesium and hydrogen, are going to switch spots. Okay, so that means we got H, and if H is by itself, it's going to be a diatomic element plus Mg and Cl. I know chlorine's -1 charge and magnesium 2+. If I forget, I can look at the back of my periodic table. I crisscross it, so it should be MgCl2. 2 Cl's, 2 H's, put 2 coefficient, 2 Cl's, 2 H's, and we got it. States of matter. I know magnesium is a solid because I saw it with my own eyes. Hydrochloric acid is aqueous. Then we got H2 is a gas, and MgCl2, again, aqueous. Alright, so we want to determine the pressure of the dry hydrogen in millimeters of mercury. We said that the total pressure was 768 millimeters of mercury. This is going to equal the water vapor pressure of 15.5 plus P of the H2 gas. And where am I getting those two values? 768 total pressure, 15.5 partial pressure of the water vapor. I subtract these numbers out. 768 minus 15.5. 752.5. So that's my partial pressure of the dry hydrogen gas. I don't want to determine the number of moles of H2, so this is where I'm bringing stoichiometry. So, I'm bringing that predict the product from term 1, balancing the equation. I'm doing stoichiometry. I got to start with a certain number, 0.0282. That's my mass of magnesium, 0.0282. 0.0282. Did you hear that? Minecraft convo. Okay. Guess it's passing period right now. Sorry about the back noise. We got 0.0282 grams of magnesium. We want to first convert this to moles. And I know that there are 24.3 grams of magnesium in 1 mole of magnesium because I know my periodic table. If you're not sure, you can go to it. It does say 24.3 right there. Don't believe me, you can look it up. 0.0282 divided by 24.3. That's going to give me 0.00116 moles of magnesium. But we don't want moles of magnesium. We want moles of hydrogen. That's what it's asking for. So we got to do the Molemole ratio. So it's write a balanced equation, write down given, convert to moles, step 4, Molemole ratio. And we want to convert it to H2, and we're getting rid of magnesium. So then we go back to original equation. H2, there's just 1, and Mg, there's just 1. So it's a 1 over 1 mole ratio. I multiply those out. My number doesn't change, but my unit does. No longer am I in magnesium, now I'm in H2 gas, which is what the question was asking for. All right. Next, we got to determine an experimental value for R. So this is where we do the ideal gas law. Finally, my pressure is 752.5. My volume is what I'm going to get from my Udeometer. So I'll come back to that one. My moles, N, is 0.00116. And let's see, my R. That's what I'm looking for, R. And my temperature, going back, is 18, but we got to be in Kelvin, so we add 273. So 273, 83, 93 minus 2, 291. All right, now before we can do anything more, we got to see what our volume is. So it might be a little soon yet. We'll take a look at what our experiment is showing. And I was correct in that. I'm not done yet. You can see that there's a lot more volume produced, but there's still a lot more H2 gas being produced, and you can see those bubbles sliding up. So we're going to have this sit for a little bit longer. Still see quite a bit of magnesium left. And I will start, I'll unpause this video once it is complete. Alright guys, what we got going on, let me make this bigger here. Looking at the results here, you can see a bunch of, just a bunch of air, hydrogens kind of sticking there. Overall, we got a good amount of hydrogen produced. So what we're going to do now is I'm going to take this without getting any air bubbles. I'm going to plug this bottom with my finger, and I'm going to put this into my graduated cylinder, and I need the water level of the Udeometer to match the water level in here. All right. And whoops, you could probably see that, a bunch of little air bubbles. That was a bunch of air that just happened. And so this water level, as you can see, maybe not as much. It goes up and down depending on how far this goes, because I'm changing the pressure in there with each drop or raise of this Udeometer. So I need the water level in the Udeometer to match the water level in the graduated cylinder. And when I do that, I can then measure the volume in the Udeometer. Looks like 27, 28, 28.5. All right, 28.5. So we're going to remember that. Let's bring this over to the calculation sheet. 28.5. So I'm going to put this here, 28.5 milliliters. But when we're doing this, we need to be in liters because that's what our R is in. So 28.5 milliliters times 1 liter over 1,000 milliliters is essentially going to be 0.0285 liters. All right. And then from here, we're going to divide both sides by 0.00116, and 291. 00116 and 291. 752.5 times 0.0285 divided by 0.00116 divided by 291. Looks like 63.5 is our R. And wait a minute, that's looking like really close. 62.3 is our accepted value. And we got 63.5. Who got this data? Oh my gosh. They're good. Let's get rid of that. Okay. Oh, now we got to do accepted value. Okay. So our accepted, or percent error. So our accepted value is 62.3 and our experimental value is 63.5. So it's accepted minus experiment divided by accepted times 100. Our accepted 62.3 minus experiment 63.5 divided by accepted 62.3. And it's the absolute value. We multiply it by 100. Right, so 62.3 minus 63.5 divided by 62.3 times 100. And it's absolute value, so it's positive 1.9%. Now that is a really good experiment. Well done. I'm really proud of this person's data. So that's pretty much it. What we calculated was the R, and we did it through experimentation. So where does R come from? It's this magical number that makes this equation work, and it's experimentally determined. We just confirmed it utilizing stoichiometry, our knowledge of the law of conservation of mass, and predicting products and balancing. This is real chemistry. So that's all I have besides cleaning up. So I'm going to mop my table down, pour out my Udeometer, and make it look spick and shine for the next group, just like you always do. That's all I have. Have a great day, and see you next time.